Hi, and welcome back. Today, we're going to be doing some pre-processing, looking at bad channels, going all the way through baseline correction. Last time, we filtered the data, so we're going to move on. And the first thing we're going to do is we're going to look for some bad channels. Then we're going to re-reference the data, epoch it, and baseline correct it. It seems like a lot, but actually some of these steps are quite short, so won't take us too long to do. The first thing we're going to do is we're going to look for bad channels. This is basically when an electrode is not collecting data or is collecting really noisy data. So this can look like a flat line like you see here, and that's when the electrode really just isn't collecting data at all. It can also look like a channel that is moving drastically up or drastically down. Channel in this sense is really just an electrode that's not collecting well. And so that would not be good. It means our data is basically going out of range. But it could also be that it's just really noisy data. There's a lot of high frequency noise in there. People talk about this as looking like a hairy caterpillar, and that's just bad data. It's not going to be good to look at. It's okay to have a couple of bad channels, but the recommendation is if you have more than 10% of your data that's from bad channels, that you really ought not to be using that participant. So if you have a small system, like a 32 channel system, you can afford to have 2 or 3 bad channels. If you have a larger system, you can afford to have more bad channels. There are basically 2 ways to deal with bad channels. One is simply removing the channel from analysis, and this is something you can do later along in the process. This is best when there's a small set of electrodes, 32 or under. The problem with this is you can't do this if the participant you want to use has a bad channel that is of interest to you. So for example, if I'm doing an N400 study and I want to look at the activity at CZ, but my participant has a bad channel at CZ, I can't use that in data analysis, and I can't use that participant in that analysis. The other option is interpolation, or interpolating the channel. This is really best when you have a larger set of electrodes, 64 or more. Here you're using information from other electrodes to make a best guess or a best prediction of what would have been seen at the electrode. This is doable because electrode signals aren't really independent of each other. So the closer they are on the scalp, the more similar those signals are going to be to each other. So that allows us to do that kind of interpolation from those surrounding electrodes. For the purposes of today and our practical aspect, we're just going to be identifying those bad electrodes. I'm not going to be showing you how to interpolate, as that's a little bit more advanced. After we do this, we're going to move on to re-referencing the data. Re-referencing allows you to change the reference type from whatever was used during the recording. Sometimes recordings are done without a reference, or you don't know the reference, or you just want to change it. There are multiple ways of referencing. So you could use the mastoids, which are the bones behind your ears that are big and thick, and they don't let a lot of electricity through. You could use an average reference across the whole head. You take the average of all the electrodes. You could use tip of nose, earlobes, etc. But choosing a reference is really important because it does different things to your data that you might be concerned about. So electrodes measure neural activity across the scalp, but mostly they're measuring activity closest to the electrode, or what's closest to the electrode is going to be at least the strongest, right? So if the reference is too close to an electrode of interest, it can subtract out some critical neural activity that you care about. A good example of this is the N170. So the N170 is a component related to face processing. And if I'm interested in the N170 and I'm using a mastoid reference, which is, as I said, behind the ears, the N170 is generated in the temporal cortex. And so if I'm using the mastoid reference, it's going to attenuate or make smaller that activity, as you can kind of see here in the dotted lines. If I'm interested in the N170, I'm probably going to choose an average reference instead, which uses the entire scalp and the average of that, because then I'm getting a much larger amplitude N170, and it makes a pretty significant difference. So you do want to be aware of what's used for your particular component of interest generally, and make an informed decision about what kind of reference you're using. Also, it's important to note that references can reverse the polarity of a signal, so it can really change what you're actually looking at. Another thing you can do along with re-referencing, if you happen to be using equations to do your work versus a computer plugin to do your work, you can create something called a bipolar channel at the same time. Bipolar channels can be created to make eye artifacts easier to detect. And they're created using simple math. Because the eye channels are opposite in polarity, you can just use some simple math to create these nice bipolar channels. So for example, if you wanted one that was looking at your vertical eye movements, you could take the vertical eye oculogram and subtract the lower from the upper to get a nice bipolar channel. For the horizontal, you could do the same thing, but using the right minus the left. This is something you can do in channel operations in ERP Lab, but if you're using the more automated process, you wouldn't be able to do this. But this can be really helpful when you're trying to detect blinks and eye movements. The next step is epoching the data. So epoching the data is really just taking that very long electrophysiological data set that's continuous and breaking it down. As you're collecting the data, you should also be sending codes or triggers or markers, whatever you want to call them, that indicate the occurrence of a stimulus and or a response. And so those little markers are in your data, and we want to use those to actually break up our data into segments or epoch it. Epoching extracts those fixed length segments of data, and it's using those markers to time lock them to event codes of interest. This is necessary if you're going to be doing that averaging step so that you can compare conditions. Epochs include typically a baseline period as well as a trial period. The baseline is usually 100 or 200 milliseconds before whatever stimulus happens, that event code, whether it's a stimulus or a response, and then a trial period, which is the time after the event code, usually around 500 to 1500 milliseconds. At the same time you're doing that epoching, you are doing a baseline correction in ERP Lab. So baseline correction is helping us to adjust our data because there's stuff going on before our event. So we've just broken up our data into smaller segments, right? And we want to have those segments be aligned so that we can compare them in a better way. What we are doing with baseline correction is we're eliminating the noise in the baseline period and removing these uninteresting signals from the waveform. So we're taking the mean of the pre-stimulus period, this period before the stimulus, before the zero, and we're subtracting that mean from the waveform to basically adjust our waveform so that we're looking at our data as if it started at zero when the stimulus came on the screen or when you had that response. So it's adjusting each segment so that the baseline, assuming nothing was going on at baseline, we get rid of all that noise and we're starting at the same reference point. The baseline period can also be chosen, it doesn't have to be in relation to the stimulus. It could be in relation to something else like the response. And so you might need to choose a baseline period that makes sense given whatever it is you're looking at. It's typically performed after the epochs are extracted from the EEG data rather than beforehand. We do this because anything that influences or creates noise in the pre-stimulus baseline period, it's also going to have an influence on what's post-stimulus, what's actually happening. And so you want to try and get rid of as much of that as you can. It also can address drift caused by skin hydration or skin potentials, things like that. It works well to minimize offsets due to just kind of gradual shifts over time in the electrode. And also information prior to the target influences the voltage and is unrelated to the condition being studied can be reduced, right? So these are all the reasons why we want to do that kind of baseline correction. So those are the steps we're going to walk through. I'm going to change my share now so that we can actually do the practical stuff. And I'm going to go to my whole screen, even though it's still black. Give me a second. So we're now going to go back over to MATLAB. I'm going to pretend we're starting from scratch again, but I'm going to go much quicker. So if you're starting again at this point, you want to make sure you set your path to wherever your EEG Lab, ERP Lab plugin is. And I do this because sometimes people are starting again and they've forgotten they need to do this step. So we're going to go ahead and set our path. Don't need to save it. I'm going to go ahead and open EEG Lab. Take a second to come up. And if you're starting with a new file and you haven't just moved on from the last video, you're going to have to open up your raw data. And again, we're using the raw data from Brain Vision. And I'm going to be using the subject 1070, which is an N400 subject. I'm going to go ahead and click OK. And I'm going to give it a name, 1070. And in order to look at or look for bad channels, I actually do need to filter this first. So I'm not going to go through this in detail, but I'm just going to remind you of how you would do a filter. You go to Filter and Frequency Tools within ERP Lab, Filters for EEG data, because we haven't segmented the data yet. And I'm just going to use a basic default Butterworth filter from 0.1 to 30. That's a good one to do this at. And so I'm going to go ahead and apply that. And it's going to ask me to save my old data set now that I'm creating a new one. And so now I have my filtered file. And now I'm going to actually plot that because I want to look for any possible bad channels. You want to make sure that your scale is one that makes sense. You might use 50 or 75, but something where you can actually see what's going on in the electrodes. And you don't want to just look at this first time frame. You want to look at various points in time throughout your data. I'm not going to scroll through the whole data set, but just to give you a sense of how you do this, you could go second by second or a couple of seconds at a time. Or you could say, I want to skip ahead to 300 seconds in, and you could look at 300 seconds in. At the moment, I don't see any bad channels in this, but you might. And so the only way to know is to kind of scroll through the whole thing and make sure it's generally staying okay. So after I've looked for my bad channels, the next thing I'm going to do is I'm going to re-reference my data. As I mentioned, there are two ways you can do this. One is an automated process, and one is using a file with mathematical equations. We're going to use the mathematical equations ones because I want to create some bipolar channels. If you are not doing that, you could use the automated process that is a tool within EEG Lab, and you just go to re-reference the data, and you could compute the average reference, or you could select re-reference to specific channels, and you click on these little dots to get to which channels. In my data, that would be the mastoids TP9 and TP10 on my system, and click OK, and it will populate that. If you are using Recorder and you aren't recording with a reference, you might need to retain the reference channel. That's a little bit more detailed process, but you would have to click this and you'd have to tell it which channel to add the old channel back. So you would put in, say if it was FCZ, you would have to add that back in. I'm not going to do that today, but I did want to show you that it does exist if you don't have a file that has the equations in it. We do have such a file. And the reason we're using it is because we are going to add in those bipolar channels. So instead, we're going to use EEG channel operations, which is under ERP Lab. And your screen may have a blank here. I've already loaded my file, but you would want to either create these mathematical equations, or if you're using the Pursue data set, you could load ours. And so you go to Load List. and you'd go to wherever you happen to have your equations. Ours are called pursue mastoid ref. And that would pull up these different equations. All these are generating the mastoid reference. So it's taking the average of the mastoids and subtracting that from each channel. But it's also creating these bipolar channels at the bottom here. And so it's doing the same math that the automated process would do as well, just with some additions. So once I have this loaded up, I can go ahead and run. And you'll see in the background, it's doing some work and it's plugging along. Once it's done, you'll see the 2 arrows. It's not moving anymore. And it's going to ask us to save it. I often will save with the prior name, just so that I know that I have it. If I wanted to save it to my computer somewhere in a hard file, this save on the bottom is just in the program. The top save is on my hard drive somewhere or in the cloud somewhere. And just as a reminder, it's going to add on what we've just done. So I had already done the filter and it called that filt, and now it's added chop. Chop just stands for channel operations. So I did some process. In this case, it was re-referencing. I'm going to go ahead and click OK. And now I have 3 data sets. I have my raw, my filtered, and my re-referenced. The next step is I want to epoch my data. Epoching actually takes a number of steps. So the first thing we need to do is we need to look through our data set and see which codes are in there, which triggers are in there. And so we're going to create an event list. And just in case you missed that, I'm going to show you that again. We're going to create an EEG event list. And it's going to warn us that there are some codes, and that's fine. And my data have some S's that it doesn't like. So it's going to pull up a window. It's going to ask you if we want to export this somewhere. And it is a good idea to export the list somewhere. I'm just going to call it assign events, so I know what it is. And I'm going to put it on my desktop so I know where it is. You want to give these descriptive names so you know what you just did. I'm also going to add in a code for boundary events. This is just to indicate this was the beginning of the recording. And that's about it. And I'm going to go ahead and create it. So this is just creating a list of all the events in my file. It doesn't like some things in terms of like the names. Don't worry about it. Go ahead and overwrite. That's fine. That warning always comes up for me. And then we're going to go ahead and save this. And I'm, again, just saving the last data set, so I still have that. This is now filtered. I've done my re-reference, and now I've created an event list. Go ahead and click OK. The next step, once I've created my event list, is I'm actually going to tell the system what those events mean, right? So we know, say, a 1 code might be a related word. Well, I need to actually put that in my file. So we're going to use what's called a BDF file or a bin descriptor file to tell us what those codes mean. So you're going to need to navigate to find yours. I happen to already have navigated there. And in this case, it's an N400, and I have a BDF file that specifically has those codes. And you'll see this in a later step. So I'm going to go ahead and open that one. I'm going to be doing this on the current data set, and I'm going to be then writing this new file to a name, and I'm going to call it 1070 event list, because I'm going to use that in a minute just to look at what I've got. So I'm going to go ahead and run that. And now I've got a new thing. I've created my list and I've assigned bins to it. And I'm going to go ahead and click OK. And so now I am on data set 5. I now have my bins assigned. Before I actually do the extracting of the epochs, I'm going to do one last thing, and that's visualizing it. I'm going to see, do I actually have all the bins I think I need, and are they all in the right place? So I can use the BDF visualizer to do that. And I have to do a couple things. I have to load an event list and load that BDF file. So the event list is the one I just created. And so this I happen to have put on my desktop. And this was the one I called 1070 event list. So it was the second one I created. And then I am going to load my BDF file, that bin descriptor file. And that one is the one I had over here. So I'm going to go ahead and open that one. And then I'm going to hit analyze. But before I do, just so you can see, it's just pulled up how my codes are related to my actual conditions. So bin 1 is one type of condition, and that happened to be associated with the codes 211 and 212, and there's a bunch more information. Some of these will be very complicated, some are pretty simple. This is a slightly more complicated one. But we're going to go ahead and hit Analyze BDF. And what it's going to do is it's going to tell me how many of these different things, and sorry, I get a warning you probably won't get, that we actually have. So I have 405 event codes. 60 of them are in bin 1, 60 of them are in bin 2, none are in bin 3, none are in bin 4. Happens to be that the subject did not make any mistakes. So they have only correct bin 1 and bin 2. They don't have any incorrect bin 3 or bin 4 in this case. This is a good moment to check that everything worked like you think it should. There are enough trials or the kinds of trials that you think you should have. So this is really a check step. You can go ahead and close this. And then the last thing we're going to do is we're going to actually epoch our data. So extract bin-based epochs. Now it's going to do two things at the same time. It's going to both extract our bin-based epochs, and it's going to do the baseline correction. You want to set your window to whatever your epoch window is. In this case, I'm going to set the entire epoch to 200 milliseconds before the stimulus came on the screen to 800 milliseconds after. You could change this. You could make this 1,000 or 600 or what have you, whatever your window should be. And then you can set your baseline correction to where you want it to be. You might need a custom one, but for the most part, you're going to use pre, which just means whatever that negative number you put in here to 0. And that's what we're going to use. So we're going to go ahead and hit run. And now I'm going to save my last data set again. So I have that, but I have a file now that is filtered. It's re-referenced. I've created my event list and assigned those bins, and I've now epoched it. So now I should have epoched data. And so we are now at data set number 6, and we have epoch data. And just before I let you go, I'm going to show you what this looks like in a channel data scroll. So before we had continuous data. Now we do not. We have just our trials, and these dotted lines are the breaks between those trials. So you can see at the dotted lines, the waveforms aren't exactly aligned all the time. So for example, right down here, there's like nothing coming out on the left-hand side of this line because that's a trial. And so it might have shifted around depending on what was in between. So this is where I'm going to stop. Thank you so much and good luck.